Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about factoring, specifically factoring polynomials. Always remember to factor completely. We're going to talk about various different types of factoring, and when you think you have completely factored a polynomial, check to see if you can factor it yet again using the same technique or a different technique. Just factor completely. First, we will talk about finding the greatest common factor, or GCF. So here's a very simple example. AX plus AY. If you factor out the A, which is a factor of each term, you are left with X plus Y. Here is a slightly more complex example. AB times X plus 2 times A times B times C times Y. These two terms have multiple factors in common, A and B. So the greatest common factor of each of those terms is A times B, AB. That leaves us X, if we factor it out, X in the first term and 2CY in the second term. That was my first example of using GCF factoring. Here's my second. Examining this polynomial, there's a 3 in the coefficient of the first term and a 6 here, which has 3 as a factor. We have an x squared and an x to the first power. We have a z and a z. We have one term that has everything multiplied inside it, a second term that has everything multiplied inside it. They are separated by a subtraction sign. So the greatest common factor of these two is 3xz. If we factor 3xz out of the first term, we are left with x. And if we factor it out of the second term, 6 divided by 3 is 2, x divided by x is 1, z divided by z, all we have left is the y. Now here is a polynomial expression from machine design, and you can think of the d's as diameters or distances, but the small d is different than the big D. All right, but what is the greatest common factor? Is it 4? There's a 4 there, there's a 4 there. There is not a 4 as a coefficient here. How about d squared? D squared here, there's d squared inside of d cubed, there's d squared inside of d to the fourth. Okay, so we found part of our greatest common factor. That's d squared. All right, let's look for something else. We have d squared, we have d, all right, so there's a d in each of those, a capital D. Is there a capital D here? No. So our greatest common factor is d squared for this polynomial expression. If we divide d squared out of the first term, we are left with 4 capital D squared. If we divide d squared out of the second term, we are left with 4d capital D. And in the last term, if we factor out the d squared, we are left with negative d squared. And that was the greatest common factor, factoring. A second type of factoring is the difference between two squares, or db2s. No, really, just kidding. However, you will probably see me abbreviate this way. Whenever you hear the word difference, think subtraction. And here we have a squared, our first square, minus b squared, the second square, the difference between two squares. And it breaks out into this formula. The square root of the first term plus the square root of the second term. Put that in parentheses, and then take the square root of the first term minus the square root of the second term. So it factors to a plus b times a minus b. Let's do an example with some numbers in it. Now, before I give you the answer, I'm going to point out that the square root of 4x squared is 2x, and the square root of 81y squared is 9y. So this binomial will factor into the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. Let's check our work just to be sure. We factored to get the answer we want. Now, if we multiply those two factors and get our original expression, then we have factored correctly. Distribute every term in the first binomial to every term in the second binomial. Let's do the first, the outer, the inner, and the last. Combine like terms and voila, there it is. We did it correctly. So here is a formula, or part of a formula, that can be used to determine how much fluid is running through a pipeline. I believe I'm going to need a little more room to fit this third example. This does not look like the difference between two squares. The small r is not squared here. The small r is cubed here. We have one square in place. What do we need to do? Or rather, what do we need to do first? And the answer is factor out the greatest common factor. That leaves us capital R squared minus r squared. Aha! Now we have the difference between two squares. So this, do not drop the greatest common factor. Make sure you recopy it. Here we are. Now I need to make room for our next application problem because I need a diagram. Example 4. A square as large as possible is cut from a circular metal disc of radius r. Express in factored form the area of the metal pieces that remain. Is the area that it remains not the area of the circle minus the area of the square? I believe it is. So what is the area of any circle? What's the formula? Pi r squared. What's the formula for the area of this square? We need to figure out what this side value is. That's my cursive S, so it doesn't look like I'm drawing a 5. The radius of any circle is constant. So if I draw this radius to the vertex of the square from the center to the edge of the circle, that length is also r. And since in the middle here where these two radii meet, I have a right angle, I therefore have a right triangle, and I can use the Pythagorean theorem to find the length of the hypotenuse, and that length will be the square root of r. However, that is not the area. That's only the length of the hypotenuse. We need to multiply the square root of r times the square root of r. In other words, square the side value to get the area. I already have side written as s here. Let's change that and get it written in there properly as the square root of r squared. Well, if you square a square root, you just get whatever is the radicand, r. Okay, now let's go ahead, continue to express this in factored form because that's what we were asked for. What do we have here? We have a greatest common factor of r, the radius. And that leaves us with pi r minus 1. And that's all there is to this problem. I think we have time for one more application problem. This is an applied class anyways. Let's do number 5. Now this will take a more complicated diagram. Please consider this diagram to be a cross-section of a pipe, the blue, running through a larger pipe, the green. And notice that these pipes are, have a thickness, just like physical pipes do. Such a setup might be used if a hot liquid or gas were pumped through the interior pipe, and then either there was empty space left there in the black area outside the smaller pipe but within the larger pipe, or a coolant could be pumped through that space. But here are the important dimensions that we need to discover what volume of coolant or empty space we would have in this pipe. Now, of course, with our diagram here, we're taking a cross section, and to get the volume, we would then have to multiply by the length of the pipe. But right now, we're just going to concentrate on the cross section, so we're actually looking at an area, this area. How could we calculate that area? Well, that would be the area of that larger circle outside the yellow color minus the area of the circle that's filled with black. The area of the larger circle would be pi r squared. We're going to subtract from that the area of the inner circle, which would be pi, we don't have r, but r, any radius, is equal to half of the diameter of the same circle. So d over 2 squared. So that's the formula for determining the cross-sectional area of this pipe within a pipe, okay? The area between the pipes. Let's go ahead and factor this. First thing I see that we can factor out is pi, because that's part of both terms. That's supposed to be a d there. It looks kind of funny. Anyways, are we done? No. Always look to see if you can do more. We now have the difference between two squares, which will factor in this fashion. Okay, our final answer is pi times the quantity r plus d divided by 2 times the quantity r minus d divided by 2. Time for the last type of grouping that we're going to be talking about today, factoring by grouping. So let's take a look at this. Do we have a greatest common factor? Well, there's an a and there's an a, but no a's here. Here's a 2 and here's a 2, but no 2's over here. So we don't have a greatest common factor we can take out of absolutely every term. We also have, look, an x there and an x there, but no x's here, just y's. So we're going to group this and do some factoring and see what happens. All right, so first I'm going to group these two together because they both have a coefficient of a, and these two together because they both have coefficient of 2. And now within this first binomial here that I've separated from everything else, I can factor out an a. And from the second binomial, I can factor out a 2. I still have this, I'm still adding what's here. So there's the 2, and when I factor it out of that binomial, I get x minus 2. So now I have a binomial. I have two terms because a times x minus y is one term, and 2 times x minus y is the other term. Within each of those terms, take a look. I have a greatest common factor, the factor x minus y. So let's factor that out. I get x minus y, and a is left behind. When I factor x minus y out of this second term, 2 is left behind. So there we go. We factored it. Let's do another example. It's kind of tricky. All right, so m cubed plus 3m squared minus 4m minus 12. Well, there is not an m in every term, so there's no m here. And the coefficient here is 1, so it does not have a common factor with any of the other ones. Let's see what happens if we group this. Let's group the first two terms because I see they both have m squared as one of their factors. Now this gets a little bit tricky here with the negative. I don't want to mess up my signs here. It's going to be easier for me to think about this if I change this subtraction to the addition of a negative number. It means I need to make a little more space here for all of that. And now I can remove the greatest common factors. In the first two terms, the greatest common factor would be m squared. When I divide it out of the first term, I am left with m, and I am left with 3 when I do the same thing with the second term. Then I'm going to add to that, what's the greatest common factor? Looks like it's a negative 4. Okay, and that leaves me with m, watch the sign here, plus 3. Well, look at that. That turned out pretty good because I now have m plus 3 as a factor of each term. That is my greatest common factor. I'm going to factor it out. When I factor that out of this first term that I was looking at, the entire thing, I'm left with m squared. And when I factor m plus 3 out of the second term, I'm left with a negative 4. So I'm adding a negative 4, or it's just negative 4. Ta-da! But wait, don't I have the difference between two squares there? Yes, I do. So I cannot leave it there. I must go ahead and Factor the difference between two squares. Now I can say that the original expression is completely factored. Don't stop. Keep going until you are completely done with factoring. Let's look at one more example of this. Okay, example number 3. A squared minus b squared plus a minus b. Let's see what we can do here. We could, now this is one of those cases where there are multiple ways to work the problem. So we do it one way, then I will do it another way. First, let's rearrange this. Let's put our a's together, a squared plus a, and then our b's together, minus b squared minus b. Okay, so if out of the first two terms, I'm going to do this a little bit differently in my notation. I'm not going to separate it with parentheses. You can go ahead and do that if you want to, but I'm going to find the greatest common factor of those two terms and put the parentheses in now. Okay, pull out an a, I get a squared divided by a is a divided by a is 1. All right, for the second two, I'm going to keep that negative with the b squared there, so I'm going to pull out a negative b, and that gives me b plus 1. But now that I've done that, do I have a common factor? Doesn't look like it. Well, that stinks. But that's okay. As you're working through these, you may head down the wrong path. It's all right. You don't have to be perfect the first time. Okay? Just erase it and go back. I'm going to leave it there. Just mark it out. And let's try it a different way. Because if I look at a squared minus b squared, what do I have right there if I group that together? Yeah, the difference between two squares. And we can factor that. And then if I consider these next two terms to be grouped, a minus b, that looks like I might be getting someplace. Let's factor the difference between two squares. A plus b times a minus b, and then I still have plus a minus b over here. And now, look at that. By doing it a different way, I got that a minus b to be a greatest common factor. So let's pull out that a minus b, the greatest common factor. In the first term, I'm left with a plus b. Okay, and I'm going to put more parentheses around that to show that that came together. And if I divide a minus b out of this second term, I get 1. And it's a positive 1. So I've got a lot of parentheses there. Do I really need all of them? Well, no. But I get this, a plus b plus 1 as my second term. And that is completely factored. But wait a minute. This was tricky. I should probably really check this. Okay, so I'm going to check it. I have a binomial times a trinomial. I have to distribute the first term to everything within that trinomial. So that's going to give me a squared plus ab plus a, and then I have to distribute the negative b to every term in the trinomial. And that gives me negative ab minus b squared minus b. Okay, I lined up my ab terms as I wrote those out, so it would be easier to add these. Okay, so I have a squared, and plus ab minus ab gives me 0. I have plus a, I have minus b squared minus b, which I can manipulate to get right back to my original equation. A squared minus b squared. Let me take a look down at the bottom as I read the top. A squared minus b squared plus a minus b. They are equivalent. This right here is the final answer. So here's a look at one of the problems that we've already worked through. 2 of them, 3 of them, okay, a bunch of them. Anyways, we're going to do more practice with these types of factoring in class. please study these, do the homework, look into your e-textbook and find more problems to do because we're going to learn more types of factoring and you need to be really good at factoring using these methods before you move on so you can differentiate between the different types of factoring I'm going to be teaching you. You can do it. Just practice. See you in class.